Hi everybody, this is Miss List and I'm here with 4.3, which officially is titled Representations of Reactions, but that translates to how to draw particle diagrams. So one of the aspects of AP Chemistry that they love to ask about on both AP exam multiple choice questions and AP exam FRQ questions is analyzing particle diagrams. And so this section is to introduce us to what kinds of things we should be taking note of when we do particle diagrams and things to consider. First one is relative location. So this has to do with phases of matter. If I have something that is a solid, we're going to want to draw those particles really packed in close together and have ordered. If I have liquid particles, they should be close and touching, but not in any particular order. And remember, I have gas particles that aren't touching and are spread apart. If I have something that is aqueous, I should only show the ions. Remember, aqueous means in water. I should only show the ions that would be soluble, and anything that would be a precipitate, we're going to show down at the bottom. If they ask us to draw water particles and the ions interacting with water particles, we should make sure that they're oriented the correct way. If I have a positive ion, it's going to want to orient towards the negative end of my polar water molecule, and sometimes they even have us draw those intermolecular force dashed lines. The next thing we want to be aware of is context clues. Did they mention an alloy? That's going to be a context clue that's going to help me draw my particle. Did they say it is a ionic substance? If it's an ionic substance, sometimes we will draw the positive negative. If it's a metal, then a lot of times we're just drawing the cations. These are all things to keep in context. That's why it's called context clues as we go through our particle diagrams. I mentioned before, if it's a precipitate, the solid particle should be at the bottom. And then interfaces. If I have something where I have a liquid and that meets gas particles, we want to make sure that that interface is labeled or it is obvious that that's an interface. Next, we want to make sure that we are keeping account of the number of particles. So if I have a chemical reaction, I want to make sure I'm using relative amounts. Sometimes they give us, please draw at least 5 water particles. So that would be given to us in the problem. A lot of times though, we're just giving a concentration, or we use the coefficients to help us determine how many of each thing we should draw. And then we always must observe our conservation of mass. The species in a particle diagram, sometimes it's helpful to use different shapes or symbols to identify what we have. I know it says colors here, but you're not really going to have colors available to you when we get to the AP exam, so shading can be helpful to identify different atoms or ions. We do want to make sure that if it has a charge, we're showing a charge and that it is aligned properly, especially when we talk about those IMFs. And then we want to use appropriate sizing. Atoms of the same element should be roughly the same size, and atoms that are smaller, like hydrogen, I would draw really tiny, versus something like bromine, which is much larger. So let's look at some practice problems here about representation of particles. So in this first example, they want us to draw a monoatomic element, and it doesn't give a specific requirement as far as phase of matter. So I'm going to draw these all as gas phase. If I had a monoatomic, I would show them as all around the same size, and I'm going to use one circle for one atom. If I had something that was diatomic, then that's going to be the same atom bonded to itself because it's 2 atoms. So this would be like hydrogen or chlorine. And again, I'm just choosing to draw 5 of each one just to be consistent. As a reminder, our diatomics are hydrogen and then nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Those are our diatomics. And remember, that means that when they're by themselves, they're a diatomic element. When they're bonded to a different element, then we would need to do things like draw a Lewis structure or balance the charge. So in number 3, they're asking me to draw a picture of a molecule. So I'm just going to use water, and I'm going to use open for my hydrogens, and then I'm going to shade in for my oxygen. So again, for consistency, I'm going to draw 5 of them. And they don't ask me to, but because this is water, I could also show hydrogen bonding. The hydrogen of one is going to be attracted to the oxygen of another. And similarly, the hydrogen of this one is going to be attracted to the oxygen of that one. Next, they want us to draw a mixture, and this is where I just need to show 2 distinct substances. So maybe this is one substance, and then another substance would be something like that. So mixtures would not be having necessarily the atoms. It just means more than one substance can be identified. Keeping consistent with my 5 molecule or 5 particle that I've been doing this whole time. So this is showing a mixture because I have the solid particles, and then I've got something completely different also drawn in there. All right, next one says draw a picture of a non-electrolyte in water, a weak electrolyte in water, and a strong electrolyte in water. Draw 5 particles in both. I'm going to actually start with the easiest one. Sodium chloride is a strong electrolyte. Anything that is a strong electrolyte is something that breaks apart into ions in solution. So I'm going to show 5 sodium ions separate from my 5 chlorine. So again, this is 100% soluble. That's what it means to be a strong electrolyte, is that you break up in water, you're 100% soluble. All right, 1, 2, 3, 4, 5. One more chlorine. So that's one way you can do it. Another way to do it would be, I'm going to erase these here. Another way to do it would be to include a key. So I could say solids equal sodium ion and opens equal chlorine ion. And so then it is a little bit easier to draw just because I don't have the symbols in there making things chaotic. So 1, 2, 3, 4, 5, and then 1, 2, 3, 4, 5. Again, if you're going to do it this way, you have to include a key that goes with it. So why is NaCl the strong electrolyte? We have 100% what's called dissociation. And that means every single unit of sodium chloride will break apart into the positive and negative ions. Now, a weak electrolyte is something that only partially dissociates. So a weak electrolyte is something like acetic acid. And I think, again, it would be easiest if I did the key up here. So there's my H, and then I'm going to use the acetate ion, the whole thing, as my open. So when we have something that is only a weak electrolyte, that means most of them are going to be still together. So I'm going to draw 5 of these where they are still attached. The hydrogen is still attached to the acetate ion, but then I would show 1 where they have been separated. So that's an example of a weak electrolyte. We have very little ionization. This will become important when we talk about weak acids. That's the same as a weak electrolyte. It only partially disassociates. And then CH3OH is the non-electrolyte, and that means it doesn't break up at all. So that would be no dissociation. For this one, a lot of times it's not going to break apart. And so you could, if you were doing the particle diagram with the key, you could just say that equals an open circle. And then we would just draw 5 open circles because it's not going to disassociate. Wait, that was more than 5. Another way that you could draw this one, if you really wanted to show that you understand that it's not breaking apart, you could have the CH3 equal a shaded circle, and then the OH part could be your open circle. And we're going to show all of them together. So 1, 2, 3, 4, and oops, 5. So that's just another way to represent particle diagrams. All right, let's look at our next example here. It says in the box, draw 4 water molecules with proper orientation. So here they have put a calcium ion. Calciums are positive. So I'm going to want to make my water molecules having the negative side pointing towards my calcium. And they want 4 of them. Instead of drawing it like this, if I was to draw the water molecules like this, I would need to include a key that said that the solid is hydrogen and the open is oxygen. I could also draw it as the Lewis structure. So here's my water like this, and then show the attraction lines for the hydrogen bond that way. There are more than one way to draw particle diagrams, as long as you're consistent. And if you do something like these guys, you have to include a key. So here's one where the relative amounts come into play. It says, consider the decomposition of hydrogen peroxide breaking down into water and hydrogen gas. They want us to write a balanced chemical equation for this. Hydrogen peroxide is a solution, and this is going to be decomposition, and it tells us it breaks apart into water. Water is going to be a liquid, and then oxygen gas, O2, gas phase. I do need to balance this because I do have an uneven number of oxygens on the right side of my equation. I have 1, 2, 3. So I need to get that to an even number. I'm going to put a coefficient of 2 in front of the water. And now that gives me 2 plus 2 more, which is 4. It also gives me 4 hydrogens. So I'll put a coefficient of 2 in front of the peroxide. Now we have a particle diagram, and they want us to show the breakdown of how this goes. And so 2 of the peroxides, these guys, so 2 of them are going to make 2 waters. So I'm going to draw 2 water molecules based on the key, 1, 2. Actually, I just messed up. I was thinking all the gas phase, but it says it breaks down into water. So I actually should show my water molecules down here. So 1 water molecule, 2 water molecules, because I'm using the coefficients. 2 peroxides, 1, 2, is going to make 2 water molecules, 1, 2, and then the coefficient of 1 would be implied in front of oxygen. So remember, oxygen is one of my diatomics, so I'm going to show it up here as the gas phase diatomic. Because I had 4 molecules, then I can actually make another set of it. So we can think of it as 4 peroxides are going to make 4 waters and 2 oxygens. So I need a second oxygen, and I need some more water particles down here. And I'm drawing them how they would line up with their IMFs a little bit. All right, let's look at, I think, last example. It says, consider the particle diagram below. They give us the particle diagram and they want us to write what's happening. It says that takes place between Q and N. So Q, they've told us, is the shaded, and that looks like a monoatomic element. So Q plus, I have, the N looks diatomic the way it's drawn because there's 2 atoms together. So I'm going to represent that in my diagram, or in my balanced equation. And then what are we making over here? We are making N and then 2 Q's attached. So this is N2, no, I did that backwards. Apologies. I'm making N with 2 Q's attached, so that should be NQ2. Now I do need to balance this now that I've written my equation. So switch just to another color. I've got 2 nitrogens, so I'd put a 2 here for the nitrogens. But now that gives me 2 times 2, which is 4 of the Q's. Now I need to come over here and look at my particle diagram and see our ratios here. 4 Q's, so that would be 1, 2, 3, 4, can react with 1 nitrogen. And that's going to give me 2 of my particles at the end. So again, we have that mole ratio I'm going to take 4 of my Qs and 1 of my nitrogens, and that's going to give me another 2 molecules. And what we have left over is we have 1 unused Q. And so that means that nitrogen would have to be my limiting, or I guess it's not technically nitrogen. We'll just call it N2. N2 is the limiting. And how do I know that it's the limiting reactant? Is because there's none left over. And then they don't ask me, but just because I'm extra, it does, the excess would be the leftover Q that doesn't get used. So excess reactant is Q because there is some left over. All right. Oh, that wasn't the last example. I apologize. We got a whole nother page of examples. So stay with me. It says particle diagram on number 9. It says the particle diagram below represents a mixture of hydrogen and fluorine gas in a reaction vessel. The reaction occurs according to the equation above until one of the reactants is completely consumed. In the box to the right, draw a particle diagram that represents the contents of the reactant vessel once the reaction is completed. And then represent the hydrogen and fluorine as shown. So up here, we do have a balanced equation. 1 hydrogen and 1 fluorine are going to make 2 HFs. When I come down here to do my particle diagram, I'm going to take 1 hydrogen and 1 fluorine, and that's going to create 2, and I want to make sure that I show F is a little bit bigger. That's going to make 2 HFs. And then I repeat that until I run out. So again, 1 hydrogen, 1 fluorine is going to make 2 of these guys. 1, 2, and then 1, 2. And then it looks like I have enough to make 1 more set. So 1 of each of them makes 2 HFs. We also do need to represent what's left over. So notice I'm just going to switch colors so it's easier to see. We do have 2 unused hydrogen gas particles, and I'll need to include them in my particle diagram over here. So I'm going to show the 2 unused hydrogens. On this one, it's a very similar type of problem, except we are working backwards. It says H2 and N2 are going to combine to make NH3. And they want us to work backwards to figure out what is going on in before the reaction. I would like to start out with a balanced chemical equation. It's H2 plus N2 goes to NH3. I do need to balance this, so I'm going to put a coefficient of 2 out front. So that gives me 6 hydrogens, so that means this is a 3. And then 1 in front of nitrogen is implied. Now that I know what my coefficients are, I can work backwards to figure this out. So 2 of these guys is going to end up giving me 3 hydrogens and 1 nitrogen. Now I do also have this guy that was left over. So let's not forget him. I'm going to draw him first before I start adding to this. So that was my leftover one. Now I need 3 H's, 3 more hydrogen gases drawn. So 1, 2, 3. And then I have 2 nitrogens. So my nitrogens are going to be a little bit bigger. And then I have enough to make a whole nother set. Here are my 2 NH3s. That is going to be 3 hydrogens. Usually we want to mix these around, especially if they're gases. We know that they're going to be moving around. So there's my 3 hydrogens, and then I need 2 nitrogens. So 1, 2. I didn't do a very good job of mixing those around in the box, but that's okay. Here we have a couple more examples, and these involve a precipitate in my reaction. So it says that first we want to write a balanced equation. We've got NaCl, and it says that that's aqueous, and I'm going to be reacting it with AgNO3, and that's aqueous. This is an example of my double replacement reaction. So Na and NO3 are going to go together. Na, NO3. And remember, both Na and NO3 are snap ions, so those are going to not be my precipitate. They're going to remain aqueous. And then Ag and chlorine go together, and that's going to form my precipitate. we have a 1-to-1 ratio across the board. So 1 NaCl and 1 silver nitrate is going to form 1 NaNO3 and 1 AgCl. So down here at the bottom, I'm going to show my Ag, and I'm going to use the same consistency that they did. So Ag and then Cl, and then I'm going to draw my Cl opposite of another Ag. There is my precipitate, and I'm even going to label it AgL, solid. And then the rest of my particles that did not get used in the reaction, we talked about this when we did net ionic equations, those are remaining aqueous in solution. So I'm going to show those just hanging out above as spectator ions. Another way you can represent the precipitate in the bottom instead of drawing it like ions like this, I've also seen someone or on the college board where they just write solid like this, and they write it as AgCl solid. So this is where we would have to use our context clues as to how they want that solid to be represented. If they said something along the lines of make sure to show every particle, then I would do the other one where I showed each individual sodium chloride or silver chloride. So now we've got some just last couple practice problems here with double replacement reactions. I have K2SO4 plus lithium hydroxide, and that's going to form its double replacement KOH. It's outsides and insides, and then lithium is going to go with sulfate. When I balance this though, I have 2 potassiums, so I need a 2 here. Then I'm going to need 2 hydroxides, and that ends up helping me because I needed 2 lithiums. Now the key here is making sure that the number of things is correct. So for example, in my left one, I have 2 potassiums. So I would need to draw 2 potassiums, and then I would only draw 1 sulfate. And here I have 2 lithium hydroxides. So that means I need to draw 2 lithiums and 2, oops, getting a little crazy with my diagrams, hydroxides like that. Now on the right hand side, potassium is one of our snap ions, so KOH is going to be still an aqueous, and since they've only drawn 1 box, that makes me think that lithium sulfate is my precipitate. Over on my product side, KOH is going to remain aqueous. Lithium and sulfate are not in the always soluble. There are some sulfates that are insoluble. However, this is not one of them. And so in this one, I would actually have to consult my solubility chart, and you would find that actually lithium sulfate is soluble. So in this one, I'm not going to have any precipitate at all. I'm just going to have all my free-floating ions. So I'm going to have 2 Ks, 2 OHs, 2 lithiums, and 1 sulfate. And then you can put circles around them to show that they're ions if you would like. So this one actually would not show any precipitate. Keep in mind that that's a kind of tricky molecule. That's not one that you're expected to know is soluble or insoluble unless your teacher has you memorizing all of the solubility rules. Remember, we want to pay attention to the snap ions as being always soluble. And usually that is enough of the solubility rules to get you through. So now on the next one, we've got another double replacement reaction. K and Cl are going to end up together. K is one of my snap ions, so I'm going to go ahead and mark that aqueous. And then calcium and phosphate are going to go together. Ca3, PO4. This is going to be my precipitate. So I do need to balance this. I have 3 calciums, so I need a 3 here. And then I have 3 potassiums, so I also need a 3 here. That's going to give me, actually, I'm messing up already. Let's start over. I do need to balance this. I have 2 phosphates, so I'm going to need to put a 2 here. That's going to give me 6 potassiums, so I'll need to put a 6 there. That also gives me 6 chlorines. So I'll need a 3 here, and that ends up helping me because I needed 6 chlorines as well. So in this one, again, we do need to take into account our coefficients. So I'm going to be drawing 6 potassiums. And just for time, I'm going to leave the circles off. So 6 potassiums, and that 2 carries to phosphate. I'm going to show 2 phosphates. The next one, I'm going to show 3 calcium ions. It's important whenever you're doing an ion that we include the charges of the ion. So 3 calciums and then 6 chlorines. 1, 2, 3, 4, 5, and 6. And then in our resulting beaker at the end, our spectator ions are going to be 6 potassiums and 6 chlorines. And then I'm just going to show my precipitate down here as kind of a big chunk at the bottom. Sometimes we abbreviate precipitation as PPT, is a common abbreviation. So I'll need to show my spectator ions, and that's going to be 6 potassiums. 1, 2, 3, 4, 5, 6, and 6 chlorines. All right, guys, I know this was a little bit longer of a video, but it is super important. Particle diagrams show up in almost every unit, and this was just a little introduction to it, and I hope you find it helpful. Thanks, guys. Bye.